All right. Hello everyone. I am going to be recording. I'm going to be going over the practice exam for your midterm one for this class. And aside from going over the practice exam for this class, I'll be going over some details which are important for you to know as you solve the problems on this exam. So this first exam covers module 1 and module 2. Module 1 basically focuses on vector coordinates, vector transformations, dot products, cross products, using the right hand rule, knowing the difference between a vector point and a vector field, and most importantly, conversion from Cartesian to cylindrical, Cartesian to spherical, cylindrical to spherical, and vice versa as well, for which you're given a table, but I will go into further detail of that as well because it's important to know how to draw these as well at the same time, because there will be several occasions where the table alone will not get you through that. And the second module focuses more on the vector calculus, which you'll cover in your Calculus 3 class, where you will be doing field integration and converting to spherical coordinates. And you'll be integrating along various vectors to find vectors and vector lines to find magnetic flux, scalar fields, and basically expressing the vector field in various coordinates and formats. So you were given the practice exam, which I believe you should all have worked out by now. And okay, I'm going to go ahead and share a blank notepad with you. And hopefully you can see this black notepad. If we're not able to see it in the recording, I will share the PDF of these files with you as well. So your practice exam has 4 problems first, and I'm going to be just a moment. Solving each one of them. So the first problem is asking you what looks like a simple vector subtraction and vector addition, finding the magnitude of the vectors. But there are some other details I do want to go over with relation to this problem. I'm going to write the problem first. 2ax plus 6ay minus 3az and you're given a second vector field, b equals to minus 3ax minus 4ay minus 5az. And you are asked to solve for three different things. You are asked to solve for a minus b, the magnitude of a plus b, and the magnitude of a plus 3b divided by a plus 3b divided by b. First of all, before I go ahead and solve this problem, I wanted to iterate to you that, and this is something that you should be careful about, is that I can express something as 2, 6, minus 3 like this. And you should be familiar with this as the x-coordinate, y-coordinate, and z-coordinate of a plane. And I can express this as minus 3, minus 4, minus 5. These are not equal to 2ax plus 6ay minus 3az. And minus 3ax likewise. Minus 3ax minus 4ay minus 5z. These are not equal to each other, because one is a specific location, and that's this. These are specific locations. These are the entire space or the region within which these specific locations are found. So that is why you cannot say that this is the same as this. This is a vector field. And this is a vector point or vector coordinate. Now, some of the basic rules which I'm sure you are aware of or that you will be using for this first problem is that you know that a minus b in vectors is the same thing as b minus a. A plus b is the same thing as b plus a. Okay. And the third thing which you'll be aware of is that the dot product a dot b is the same thing as b dot a. So for this particular problem, if I want to find out a minus b, Just what I would do is I would subtract the two x coordinates, I would subtract two y coordinates, and the two z coordinates given to you. So that will be 2 minus minus 3 plus, oh, sorry, not plus, minus 2 minus minus 3 minus 6 minus minus 4 minus 3 minus minus 5. And then you have a z, a y, a x. So that will be 5ax minus minus 10 plus 10 ay minus 2az. Oh, sorry, plus 2az. And that will be the answer to part 1. Then the next part of the question, you are asked to find a plus b, and then you're asked to find the magnitude of a plus b. So part B is first thing you got to find a plus b. You know that a plus b will be the same thing as b plus a. So a plus b is equal to 2 plus minus 3ax. So 2 plus minus 3ax plus 6 plus minus 4ay plus minus 3 minus 5 az minus 3 plus minus 5 az. Okay, so that will be minus of ax plus 2ay minus 8az, and we'll put caps on top of each of those. And you know that the modulus of this is going to be the square root of minus 1 square plus 2 square plus minus 8 square. And that will be 1 plus 4, 5 plus 64 is 69. So the square root of 69, which is the answer to that problem. Okay, then on to part C. Part C is asking you the modulus of a plus 3b divided by the magnitude of a plus 3b times the magnitude of b. So the first thing you're going to do is you're going to solve for a plus 3b. There's actually a long way and a short way to going about this question. You can easily realize that this expression is basically asking you the short form of of a rule that exists in vector calculus, which involves calculating using the magnitude of a vector that you're given and using that to calculate the specific directional vector. So What you notice is a plus 3b divided by square root of a divided by modulus of a plus 3b. What you see here is that the mod of a plus 3b divided by the mod of a plus 3b is going to be 1 basically. So this whole expression ends up becoming 1 times b bar. So you're just left with b bar basically. And you're quite the question asked for the no, and the question didn't ask for the magnitude, so I have to make a small correction here. So let's erase these signs to avoid confusion. It didn't ask you the magnitude. So the answer is basically the same thing as whatever your vector b was. So that's minus 3ax minus 4ay minus 5az. And you put caps around all of those to indicate that these are vector fields and not specific locations. And that should be the answer. The long way of going about this whole thing would be to find the magnitude of a plus 3b, then add a plus 3b, divide the two, you would get a specific directional vector. You would multiply that directional vector, or rather take the dot product of that directional vector with the dot product of b, only to realize that whatever answer you were going to end up getting, everything was going to cancel out and you were going to be left with this. I'm not going to do that because I just here, but that will be the very long way of doing it. The easy way would be to realize what properties at play here and what you can cancel out easily to shorten this expression into as short a format as possible. With that said, there are some other rules that surround vectors and vector cross products. So I already mentioned that the dot product of two vectors a dot b is going to be equal to b dot a. To go a step further from that, we need to know that when the dot product is equal to either -1 or +1, or it's between the two values -1 and +1. So -1 and +1 is less than a dot b is less than 1. This means that your dot product is normalized. The vectors are normalized. The vectors are normalized. That's one good thing to remember. The second thing to remember is that if I have the dot product a dot b is the same thing as saying whatever x coordinate multiplied by x of the x coordinate of a with the dot product of the x coordinate of b plus the y coordinate of a with dotted with the y coordinate of B plus the z coordinate of A dotted with the z coordinate of B. Another way you can calculate the dot product is if you're given a particular angle, you can take the cosine of that angle, and if you know the coordinates, you know the value of each component. The next thing to remember, which will be more useful in the next problems on this exam, is A cross B. A cross B, which is the cross product, and that can be calculated using the right hand grip rule. Right hand grip rule. So basically, you point your thumb upwards. You have your second finger, and you have your third finger. You have your third finger, and Imagine a spear between each of these fingers. You move the thumb in the direction of your vector field, and you put your second finger in the direction of the other vector. You will see that the thumb is pointed towards the direction of A cross B. So that is the right hand rule. That is the right hand rule. The other thing you need to remember is the projection of B onto A, and the projection is equal to B dot, I'm going to switch to my pen now, B dot A multiplied by the direction of A cap, which will be equal to the magnitude of B dotted with the magnitude of A times cosine theta. Also, be aware that A cap is the same thing as A is the directional vector basically. So it's A divided by the modulus of A, which is basically the magnitude of A. And of course, the same thing with B, C, whatever. Yeah. And in a diagram, how you would visualize this projection is, imagine if you have two angles, two vectors, sorry. You have a vector A and you have a vector B. The angle between these two vectors is theta. Then you have an arrow here, and you have another arrow. So basically two arrows to indicate the direction. So this is the projection. I am trying to project this angle B, this vector which I've circled. I'm trying to project this onto A. This is the projection of B onto A. Now, another problem which you were asked on your homework, which I'm gonna go over here, is proving the law of cosines. And you want to prove that law using these definitions of vectors that you have covered. So the law of cosines, as you know, states that c is equal to the square root of a square plus b square minus 2ab cosine theta, or whatever your angle is. In this case, I'm going to call it theta. Cosine theta. So for that, I have to draw a triangle. A, B, and C. Let's say this largest angle here is theta. This is B. This is the direction of B. This is the direction of A, and this is C. Let's make a right angle triangle out of this. When I do that, I know that this is now 90 degrees. Then I know that C square is equal to the magnitude of C square, which is equal to B plus A the whole square. And that is the same thing as B plus A dotted with B plus A. Which is of course the same thing as C squared is equal to B dotted with B plus A dotted plus A plus 2 times A dotted with B. And then I am left with B square plus A square plus 2AB cosine of 180 minus theta. And how I got that is because you know the why is it cosine of 180 minus theta? Because cosine of theta is equal to the same thing as cosine of 180 minus theta. So that is b square plus a square minus 2ba cosine theta. And that is how you use vectors to prove this particular law of cosines. I'm going to go ahead and go on to problem number 2 on the midterm exam now. So problem number two is telling you that you're given a conservative vector field G xyz minus 8xy 8xy in the x direction minus 4x squared in the y direction and az. You're asked to find the scalar field such that the curl of h of x, y, comma, z, the curl, which is the negative of the gradient of h, is equal to g of x, y, comma, z. So let me just go ahead and copy paste the problem from your exam. So problem two is given here, and your job is you know that if g of x comma y comma z is equal to minus of delta h of x comma y comma z, then that means gx is equal to minus, and I'm gonna go back to pen here, minus del h divided by del z, sorry, del x, and that is the same thing as minus 8xy. You know that gy is the same thing as minus del h divided by del y. And del h divided by del y is the same thing as minus 4x squared. Then gz is equal to minus del h divided by del z, which is the same thing as 1. And I made us need to correct this. This is not z, this is x. So this, we're going to integrate this with respect to x, which means the y part's going to be 1, and we're going to ignore the y. The y part's going to be left alone the way it is. So when we do that, we get 4x square y. And this, we're going to integrate this again, and when we integrate this, with respect to y, we're going to get 4x square y. And when you integrate this with respect to z, you get z, negative z. And this is positive. This is positive as well. The rest of it stays. The rest of it is the way it is. So, and of course we have a particular constant for each of these. So I'm gonna call this C, call this D, and I'm gonna call this E. So I am left with, we notice that c of y comma z is equal to d of x comma z here, which is the same thing as minus z. So the answer is 4x squared minus 4x squared y minus z. I'm going to move this up here. Okay. Now before I go on to problem 3 is giving you a vector field and it's asking you to express it in cylindrical coordinates. The important thing is whenever you're given such a problem, you always need to make sure that you're going to draw a diagram. You can use the table, but you need to make sure that you're aware of how such derivations came about. So I'm going to take a picture from your textbook. And I'm going to take another picture from your textbook as well. Okay. So the objective of these two pictures is you're going to be converting between spherical and Cartesian, spherical and cylindrical coordinates, and more. With cylindrical coordinates, you're ranging from with cylindrical coordinates, you're ranging from 0 to infinity. So when we talk about Cartesian coordinates, we need to cover the first through eighth octants of a particular figure. And when we're having cylindrical coordinates, we need to cover from r to infinity only because we are already covering the negative y hemisphere from 0 to 2 pi. And if you have phi as the value the value of phi in spherical coordinates given to you as minus 30 degrees, you move counterclockwise. If it's plus 30 degrees, you move clockwise. And that is why when we are in cylindrical coordinates, we integrate from minus pi to pi. And that is why, because of that, we cover only the part from 0 to pi, and we do not cover from 0 to 2 pi. So theta is covered from 0 to pi by 2 on the top, and the bottom hemisphere is pi by 2 to pi. And that is why the value of phi is between minus pi and pi. So when you're converting from spherical to cylindrical coordinates, you will see that x is equal to r sine theta cos phi, y equals r sine theta sine phi, and z equals r cos theta. And when you're converting from spherical to cylindrical, r is equal to r sine theta, and q is equal to 0, and capital R is equal to capital R cosine theta. And one very important thing to note is, let's say I'm given the coordinates of r, theta, and phi. I'm given the coordinates are 8, 11, and 130. For example, 11 will never be the value of theta, and 130 will never be the value of phi in an actual problem, but let's say that's were the case. You are given in the form of, you are given it in, you cannot change r, theta, and phi and make them as corresponding to x, y, and z. No, you cannot do that. And you cannot say that r is equal to 8, theta is equal to 11, phi is equal to 130. This recording may end, but I will start another recording in case it does. And we'll continue in that recording. But if you're given r equals 8, theta equals 11, and phi equals 130, you cannot put it in Cartesian form directly. Note that capital R is different from lowercase r. Lowercase r is square root of x squared plus y squared in cylindrical format. And capital R is square root of x squared plus y squared plus z squared in spherical format.